So for this lecture, we will be discussing the norm of a vector, and we will add other operations on vectors on Rn, such as the dot product and the distance of vectors in Rn. Okay, so first, what is this norm of a vector? So given a vector v, its magnitude or length, which we will denote by this, okay, is what we call the norm of the vector v. Okay, so take note of the notation. So we have the vector v here, and it is enclosed by these two vertical brackets. Okay, so two pairs of vertical brackets or vertical lines. Okay, so we call this the norm of the vector v. So it's simply the magnitude or the length of the vector v. Okay, so if we are given the components of the vector v, okay, we have v1, v2 until vn. So this is a vector in Rn. Then this norm or magnitude or length, okay, the norm of v is given by this formula. So the components, okay, we square them and then we add them and we take the square root. Okay, so magnitude or the norm of v equals the square root of v1 squared plus v2 squared plus until vn squared. Okay, so notice that since we are squaring these components, these are all positive. If you add positive numbers or non-negative numbers, they will be, or the sum will still be non-negative. You take the square root of non-negative number, it still be non-negative. So the norm is actually non-negative. Well, it is a length or it is a magnitude. So we always have the norm of a vector to be non-negative number. And we will see that property later. Okay? So for example, we want to find the norm of each of these vector. Okay? So here, let me write the solution. So for this guy here, so we want to find the norm of the vector 2, -1, 6. Okay, so take note, I am still using these angle brackets because I am talking about vector. Okay, so the norm of the vector, okay, so this is equal to, according to the definition, this becomes the square root of 2 squared plus a -1 squared, okay, plus 6 squared. Now, I want to emphasize this middle. So common mistakes that students do is they remove this parenthesis. If you remove the parenthesis, say, let me write it here. So you have, say, -2 squared. This is equal to +4. If you remove the parenthesis, so negative and then 2 squared without the parentheses, this is equal to -4. So those two are different. Why? Because in here, the square only acts on the +2 or on the number 2. Whereas if you put the parentheses, okay, the square acts on the number -2, not just the number 2. So look at the difference. Okay, a common mistake by students is that they write -2 square as +4. So this guy here, this is mathematically incorrect. Okay, now another common mistake by student is when they have, so they have this guy here, okay, for example, okay, they have the component in here, so they write square root of 2 squared, then they forget the parentheses, so 2 squared plus 1 squared, okay? What they do is they retain that negative. So what they will get is square root of 4 minus 4 plus 2, and they will just get square root of 2. Again, it is incorrect. Okay? It is incorrect. In fact, there is a possibility that you will get a negative number inside if you don't put this guy here inside the parentheses, if it meant to be inside the parentheses. Okay? If it meant to be inside the parentheses. So what I'm saying is be careful when writing the expression. Okay? Be careful when writing the expression. Okay? So anyway, continuing. So this guy here, this is equal to the square root of, so 2 squared, that's 4, then plus. Then negative 1 squared, that's positive 1. And then plus 6 squared, that's 36. Okay? And we will get here square root of 41. Okay? So meaning the norm of this vector 2, negative 1, 6, it's equal to square root of 41. Or the magnitude of this vector is square root of 41. Or the length of that vector is square root of 41. Okay? For the second item, so we want to find the norm of this vector here. Okay, we want to find the norm of the vector 1, 5, negative 3, negative 1. So again, using that definition above, okay, we will have 1 squared plus 5 squared plus quantity, negative 3 squared, okay, plus, again, quantity, negative 1 squared, okay? So if we square them, we will get square root of 1 plus 25, negative 3 squared, that's 9, so plus 9, and then negative 1 squared, this is plus 1. Okay, and what do we get? 9 plus 1, that's 10, plus 25, that's 35, plus 1, that's 36. So this is equal to square root of 36, and if you remember, this is just positive 6. Okay, so the length of this vector, or the magnitude of this vector, or the norm of this vector, it is equal to positive 6. Okay, now let V be a vector in Rn and K be a scalar. Then, as I have mentioned, the norm of V is always non-negative. So greater than or equal to 0. You should not get negative norm. That's not possible in any kind of mathematics. Or in any kind of mathematics, the valid mathematics that we are learning, even in higher mathematics, you won't get negative norm. Now, if the norm of a vector v is 0, okay, then the vector must be 0. And conversely, the norm of the 0 vector is equal to 0. Okay, that is no other vector that has norm equal to 0 but the 0 vector. Okay, so only the 0 vector has norm equal to 0. All other vectors must have positive norm. Okay, suppose we multiply v by a scalar. Okay, so we want to get the norm of the vector kv. This is equal to the absolute value of k times the norm of v. Absolute value because your scalar can be negative. Okay, so if it is multiplied to a vector and you get the norm of that new vector kv, you have to get the absolute value of k. Okay, or absolute value of the scalar. And then you multiply that to the norm of the vector v. So take note, this is just simple multiplication. This is a number, positive number, or non-negative number. This is also a non-negative number. So you just multiply them. Okay? Questions so far? Now, a vector whose norm is equal to 1 is called a unit vector. Okay? Now, these vectors, these are all unit vectors. Why? Because, for example, let us take the norm of this. So the norm of 1 over square root of 2, comma 1 over square root of 2. So we want to take, or want to get the norm of this. This is equal to square of 1 over square root of 2 squared plus 1 over square root of 2 squared. And 1 over square root of 2, you square that, that's just 1 half. So square root of 1 half plus 1 half. Okay, so this is equal to square root of 1, which is equal to 1. Okay, so this vector is a unit vector. In fact, this is negative. So whatever, if it were negative, so negative here, you'll just put the negative in here, but you square that negative, it becomes positive. Okay. Similarly, you can check this guy here. It's also a unit vector. So we have the norm of the vector 0, square root of 3 over 2, 1 half. Okay. So this is equal to, by definition, 0 squared, okay, plus square root of 3 over 2 squared plus 1 half squared. Okay, so we will have square root of 3 over 2 squared, that's 3/4, plus 1 half is squared, that's 1/4. So this is equal to square root of 1, which is again 1. Okay, so this is also a unit vector. And similarly, this vector 0, 0, 1, 0. So obviously a unit vector. Okay, so 0 squared plus 0 squared plus 1 squared plus 0 squared. When you take the square root of that, you will still get positive 1. So the norm is 1 and it is a unit vector. Okay? Now, given a non-zero vector v, okay, we can find a unit vector which we will denote by u hat. In fact, let's just write it as v hat or u hat, whatever. Usually this guy here, okay, the hat, it tells us that it's a unit vector. Okay, so you can find a unit vector u hat whose direction is the same as v, okay, but since it's a unit vector, the magnitude of that vector will be 1, okay, and this vector u hat, the unit vector u hat, is given by 1 divided by the magnitude of v times v. Okay, so 1 over the magnitude of v, this is a scalar. So take note that this guy here, this is a scalar because magnitude of a number of a vector, it's just a number. So 1 over something, 1 over a number. And v here is a vector. So this whole guy here, it is a vector. But this is a unit vector since, look, if you take the magnitude of u hat, so note, okay, if you take the magnitude of u hat, okay, so this is equal to the magnitude 1 over magnitude of v, okay, but 1 over v, it's a scalar. So this is just the absolute value of 1 over magnitude of v times magnitude of v by the property that we have. But magnitude of v will be positive because v is a non-zero vector. Okay, v is a non-zero vector. So it is positive. So this is just what? 1 over magnitude of v times the magnitude of v. And you see that you can cancel them, this guy and this guy, and this will give you 1. Okay, so this is a unit vector. Okay, but the point here is if you have any non-zero vector, okay, you can always find the unit vector with the same direction as that given non-zero vector. And take note, we only use the non-zero vector because if v is the zero vector, the magnitude is 0. So this 1 over 0 will not be defined. Okay? So we only do this for non-zero vectors. Okay? Question so far? So find the unit vector whose direction is the same as the direction of each given vector. So the first job is we need to find the norm of each vector, and then we will be able to write the unit vector. So let me write this as our vector v. Okay, the vector v. So first, we have the magnitude of v. So by definition, this is equal to 1 squared plus 3 squared. And this is equal to square root of 1 plus 9. This is equal to 10. So square root of 10. And therefore, v hat, let me write this as v hat. So the unit vector, okay, unit vector in the same direction as v. So this is equal to 1 over magnitude of v times v. So this is equal to 1 over square root of 10 times the vector 1, comma 3. And as a vector, this is equal to 1 over square root of 10, comma 3 over square root of 10. So this is our v hat. Okay? Question. Let us look at number 2. So let me write this as w. So the vector w. So first, we want to find the magnitude of w. So this is equal to the square root of 5 squared plus negative 2 squared plus 6 squared. And this is equal to square root of 25 plus 2 squared, that's 4, plus 6 squared, that's 36. So this is equal to square root of 65. Okay? And therefore, w hat or the unit vector with the same direction as w, this is 1 over square root of 65 times the vector, okay, times the vector 5, negative 2, and then 6, okay. So as a vector, this is equal to 5 over square root of 65, comma, negative 2 over square root of 65, comma, 6 over square root of 65. Okay? So normally, you will have to rationalize this, meaning we don't want to see the square root sign or the radical sign on the denominator. But this is a linear algebra class, so I'm not interested if you know how to rationalize. Okay? Meaning you can retain this form, okay, with radical on the denominators. Okay? Question so far. Now, so from the previous slide, we said that any non-zero vector can be, we can find a unit vector whose direction is the same as that non-zero vector, okay, using this kind of formula here, okay? But in here, the next slide, we define what we call the standard unit vectors, okay? So the standard unit vectors, these are the vectors with 1 in one component and 0 in everywhere else, okay? And in the n-dimensional space, there will be n standard unit vectors. So for example, in here, we denote this by E1. And here we have 1, 0, 0, 0 all the way. And then for E2, another standard unit vector. So the first component is 0, the second component is 1, and then 0 all throughout again until the standard unit vector En. So here, all the components are 0 except for the nth component. The last component will be equal to 1. So this means the standard unit vector Ei, okay, the standard unit vector Ei, this is the vector with 0, dot, 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 then 0, 1, 0, comma, dot, 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 0. And this guy here, it's the ith component. Okay, so the subscript tells you which component is equal to 1. Okay, so for the standard unit vectors in Rn. Okay, okay. So in other words, the standard unit vector Ei is the vector with 1 at the ith component and 0 elsewhere. In the 2-dimensional and 3-dimensional spaces, we have the following special notation. For the 2 space, the first unit vector E1 will be denoted by I. The second component E2 will be denoted by J. So I and J. So first component is 1 and 0 on the second component for I. For J, the first component is 0, 1 for the second component. So I will be 1, 0, J will be 0, 1. Okay? And for the 3 space, we have I, J, and then we add K. So I will be equal to 1, 0, 0. J will be 0, 1, 0. And K will be 0, 0, 1. Okay, so I, J, K. And for 4 space, 5 space, etc., let's just use E1, E2 until En. Okay? If we have these standard unit vectors, then every vector can be written as a linear combination of the standard unit vectors. So remember linear combination? Okay? You have several vectors, there are scalar multipliers, and then you add that. Okay? So every vector in Rn can be written as a linear combination of the standard unit vectors. Okay? So how does that work? So for example, we have 1, 3. We want to write this as as a linear combination of the standard unit vectors in R2. So this guy, this 1, 3 here, actually can be written as 1i, okay, 1i plus 3j, okay? Or simply I plus 3j, okay? I plus 3j. And how is that now? How did we get this? Well, you see, this guy here, okay, this guy here can be written as 1, 0 plus 0, 3. So component-wise addition. 1 plus 0, it's 1. 0 plus 3, that's 3. Okay? And furthermore, the 3 here, we can factor out. So we will get 1, 0 plus 3 times 0, 1. Okay? So meaning, if you multiply this 3 inside this guy here, it's just 0, 3. But notice, this is your I, 1, 0. This is your J, 0, 1. Okay? So you can write any vector as a linear combination of the standard unit vectors. Okay? Similarly, for the second item here, we will get 5i minus 2j plus 6k. Okay? So 5i minus 2j plus 6k. Similarly, for 2, negative 1, 6, so you have 2i minus j plus 6k. Okay? So item 1 is in 2 space, items 2 and 3 are in 3 space. The last item here, it's in 4 space. So let's use E1, E2, E3, and E4. So this is equal to E1 plus 5E2, 5E2 minus 3E3 minus E4. Okay? So 1 times E1 plus 5 times E2 minus 3 times E3 minus 1 times E4. Okay? So if you remember, in the linear combination, when we define linear combination, we call the scalars coefficient. It's actually coming from this. So these numbers here, 2, negative 1, 6, for this vector becomes the coefficients of the standard unit vectors. Okay? Question. Okay. Now, let us talk about distances in Rn. Of course, we have a formula for the distance between 2 points in R2, okay, or distance between 2 points in R3. Okay, I hope you recall that, at least in R2, in the Cartesian plane, you recall that from your analytic geometry. Okay, maybe Sec 4 or Sec 5. Okay, so we extend that notion in Rn. And we have the same formula. So given the 2 points, P and Q, with coordinates P1, P2 until Pn, for P and Q, Q1, Q2 until Qn. Okay? Then the distance between P and Q, which we will denote by this notation here, D parenthesis P1, P and Q. Okay? So this is defined to be the square root of P1 minus Q1 squared plus P2 minus Q2 squared plus until Pn minus Qn squared. So remember, in R2 you have, say, Px1, y1, and then Qx2, y2, and you want to find the distance between P and Q. Okay, your formula was square root of x1 minus x2 squared plus y1 minus y2 squared. Okay, so we extend this notion to this part here. Okay, if we were in Rn. Okay, so recall, if the initial point of a vector is the origin, then the vector is determined by its terminal point. Okay, so let us draw that to recall. So you have the initial point to be the origin, and we have this vector v here. Okay, if this is your vector v, at least in R2, okay, at least in R2, you have your v1, v2. Okay, the terminal point here has coordinates quantity v1, comma v2. So take note, in here it's a point, in here this is a vector. Okay, so the vector is determined by its terminal point. Okay? Thus, we may write the point P as the vector V, okay, as the vector V whose components are the coordinates of P. Similarly, we may write Q as the vector W whose components are the coordinates of Q. Okay? Let me go back to that slide. So in here, you have the vector V with components V1 and V2. The point is parenthesis V1 and V2. Conversely, we are given the point V1 and V2. Okay, then we can find this vector with initial point at the origin and terminal point at the point V1, V2, and the components of that vector will be V1 and V2 also, but this time written using the angle brackets. Okay, so that's what is meant in here. Okay, therefore, in the definition above, since we have written the components or the coordinates P1, P2 until Pn will be the components of the vector V, and the coordinates Q1, Q2 until Qn are the components of the vector W, then this definition here, d of P1 or d of P comma Q, this becomes, or this can also be written as d of V comma W. Okay, d of V comma W. Okay, so it follows that if we want to find the distance of two vectors, okay, the distance of two vectors in Rn, V and W, okay, then we can use this formula. Okay, it's like finding the distance of 2 points in Rn. But notice, coordinate-wise, these are just difference. P1 minus Q1, then P2 minus Q2, and then until Pn minus Qn. Okay, and that means we have the V minus W. Okay, so first component of V minus W, it's P1 minus Q1. Second component of V minus W, it's P2 minus Q2, etc. But notice this formula, difference squared plus this guy squared plus until this guy squared, and you take the square root. Okay, so the distance V comma W is actually the norm of the vector V minus W. Okay, so again, the distance of the two vectors in Rn is actually the norm of the difference of the two vectors. Okay, question so far? So let us look at that. Yes, Melissa?
So basically, one is the distance of the 2 points, and the other one is the distance of the vectors?
Yes, because as we have said in here, we can think of the vectors as vectors in standard position with terminal points to be the points, the given points. So terminal point of V is P, terminal point of W is Q. So yes, we can think of that way.
Okay, thank you.
You're welcome. So in here, we want to find the distance between given vectors. Okay, so i.e. in notation, we want to find d of P or U minus V, U minus V, okay? But according to our analysis earlier, this is just the norm of U minus V, okay? U minus V. And of course, U minus V first. So we have the norm and then U minus V. We have 1 minus negative 2. comma 3 minus 2, and then close the norm. Or if we operate them, you have 1 minus negative 2, that's positive 3, comma 3 minus 2, that's positive 1. Okay? And this is simply square root of 3 squared plus 1 squared. And again, just simplify, you will get square root of 10. Okay? Similarly, for this distance of u and v in here, u and v, this is the norm of u minus v, okay? So this is the norm of, what do we have? 5 minus 2, comma, negative 2 minus negative 1, comma, 6 minus 6, okay? Close the vector, close the norm. So this is the norm of the vector 5 minus 2, that's 3, negative 2 minus negative 1, that's negative 1, 6 minus 6, that's 0. Okay? So again, this is square root of 3 squared plus negative 1 squared. So if you do the arithmetic here, you will get square root of 10 again. Okay? And finally, for this example, so d of u comma v, this is equal to the norm of u minus v, or this is equal to the norm. So 1 minus 0, comma, 5 minus 1, comma, negative 3 minus 0, sorry, negative 3 minus 0, comma, negative 1 minus negative 1. Close the vector, then close the norm. So if we simplify those subtractions inside the norm or inside the vector brackets, so you have 1, comma 4, comma negative 3, comma 0, okay? And then we use formula for the norm. We have 1 squared plus 4 squared plus negative 3 squared plus 0 squared. So if you simplify this, you will get 26. So try to simplify. You will get square root of 26. Okay? Question? So far, we have a vector, we can identify the norm or the magnitude. Of course, using the components, okay? And then the next operator that we had was the finding distance between two vectors, okay? Now, with regards to the direction, okay, we will have what we call angle between two vectors, especially in R2 and R3, because we have geometric interpretation for R2 and R3, okay? And if we can draw them, then we can study their angles. But this angle here, this can be extended to Rn, okay? Meaning we also have angles even in the 4 space, 5 space, etc. Okay? But how do we get this angle between two vectors? So let u and v be non-zero vectors in R2 or R3. Assume that they are positioned such that their initial points coincide. Okay, initial points coincide. just like this. This is vector u, this is vector b, this is the initial point. U, v, this is the initial point. U here and v here, this is the initial point. U here and v here, this is the initial point. Okay? The angle between u and v is the angle theta determined by u and v that satisfies the inequality 0 less than or equal to theta less than or equal to pi. Meaning, the angle between two vectors, okay, the angle between two vectors is the smaller angle between them. Okay? This guy here, you can talk about, the angle on this guy here. Okay? But this angle here is bigger than this angle, so we will not consider that. Similarly, for this second figure here, you can talk about this angle here, but again, this angle here is bigger than this angle here. This case, this angle is the same as this angle, okay? So you can talk any of that, but that's the only special case that we have. And for this angle, notice that we now consider this part here, okay? So you can talk about this angle, but we will not consider this because this is the smaller angle, okay? So it is the smaller angle between the two vectors. That will be the angle between the two vectors, okay? And which means the angle satisfies this condition. 0 less than or equal to pi, or 0 less than or equal to theta less than or equal to pi, or in degrees, this is 0 degree less than or equal to theta less than or equal to 180 degrees. Okay? A lot of times, I want the degrees to be in radians. Okay? But if you are going to use your calculator, you can use radian or you can use degrees. Okay? But make sure that your calculator has the right setup. Okay? Meaning, make sure that your calculator is in degree mode. Okay? And you will know if it is in degree mode if you would see the deg in your screen of your calculator, in the screen of your calculator. Okay? If you see rad, then that is not in degree mode. It means it is in radians. Okay? So for us, we will be using degrees if we use calculator. Okay? So just make sure that you have the proper setting in your calculators. Okay? So this is how we do it in R2 and R3. We have the geometric interpretation. Okay? We extend this to Rn. Okay? And to extend that, we actually use the R2 and R3 again. So let U and V be the non-zero vectors in R2 or R3. And let theta be the angle between them. We define the dot product, okay? We define the dot product or Euclidean inner product of U and V, which we will denote by this, U dot V. Take note of this dot here. Take note of this dot here, okay? That there, okay? It's actually there, okay? It's meant to be there. Okay, so U dot V, and this is defined to be U dot V equals magnitude of U times magnitude of V times cosine of the angle theta. Okay, so in here, let me just remind, here you have the dot product. Okay, and this guy here, this is just your usual product. multiplying two numbers or three numbers, etc. Okay? So there is no usual multiplication in vectors, space of vector, okay, or the vector space. We don't have usual multiplication there. We have what we call the dot product, okay? And later we will learn another type of product in vectors. But in here, dot product, okay, it is equal to magnitude of the first vector times usual product here, so times magnitude of the second vector times cosine of the angle between them. Okay? If u is the zero vector or v is the zero vector, okay, then the dot product of u and v is equal to 0. Okay? Take note, you have here u and v to be non-zero vectors for this formula to hold. Okay? If u is the zero vector or v is the zero vector, then u dot v, it is equal to 0. The dot product of the vectors will be 0. Okay?
So it'll
Yep.
always be cosine?
Yes, this is always cosine. This is always cosine. Okay? Other question? And take note in here, magnitude, it's a number. Magnitude, it's a number. Cosine of an angle, it's another number. So you are just multiplying numbers here. That's why it's usual product. But this one tells us that if you get the dot product of two vectors, you will get a scalar. Okay? Dot product of two vectors is a scalar. Okay? So the dot product of two vectors is a scalar. Example, the angle between u square root of 3 comma 1 and v 2 comma 0 is 30 degrees. Find the dot product of u dot v. Okay? Find the dot product u dot v. So in order to solve this, we need to find magnitude of u. Magnitude of u, this is square root of 3 squared plus 1 squared. This is equal to square root of 3 plus 1. This is equal to square root of 4, which is equal to 2. And then magnitude of v, square root of 2 squared plus 0 squared. This is just square root of 4, which is equal to 2 again. Okay? And cosine 30 degrees, if you recall from your maybe trigonometry, okay? If you recall from your trigonometry, cosine 30 degrees, this is 1/2. Yeah? 30-degree angle. So if you recall, let me just draw it here. Is it 1/2? No, it's actually square root of 3 over 2. Okay, this is square root of 3 over 2. So 30-degree angle. So you have this, and then this is your 30 degree. Okay, so x is longer than y. 30, 60, 90 triangle. So this is square root of 3 over 2. This is 1/2. So cosine of 30 degrees, it's square root of 3 over 2. Therefore, u dot v, okay, it's magnitude of u, magnitude of v, cosine 30 degrees. So this is equal to 2 times 2 times square root of 3 over 2. And this is equal to 2 square root of 3. Okay? So again, we just use this formula. Okay? Now, suppose we go to Rn. So how do we define the dot product? Initially, we don't know what angles in the space of Rn is. We don't know that one, but we can define them later. Okay, yes, Melissa.
Sorry, could I just see the previous slide again?
Yep.
Okay, so you multiply all of them and you get 2 square root of 3.
Yes.
Is that correct?
Yep, that is correct.
Okay, thank you.
You're welcome. So we go to Rn. Okay, we define dot product in Rn, but this time we define it in terms of the components. Okay, so let U be the vector with components u1, u2 until un, and v be the vector with components v1, v2 till vn. Okay, so the dot product or the Euclidean inner product of u and v, and again the same notation, u dot v. Okay, so this time we define it as you multiply component wise and then add all the products. So meaning u dot v equals u1 v1 plus u2 v2 plus until un vn. And that's it, the dot product. Component wise, you multiply them. And then you add all those products. And here, u1 and v1, or the un's here, or the ui's here, and the vi's here, they are just numbers. Okay? Ordinary numbers. So this is just the usual multiplication. u1 times v1, u2 times v2, un times vn. They are just ordinary multiplication. Okay? So example, find u dot v if we have u square root of 1 or square root of 3 comma 1 and v equals 2 comma 0. So these are the same vectors as the previous slide, but this time I did not specify the angle. In fact, the angle is still 30 degrees. Okay, but what if we don't have that information? So how do we find that product? Using this formula. So u dot v, this is equal to square root of 3 times 2 plus 1 times 0. And you will still get 2 square root of 3. Okay? 2 square root of 3. For the second problem here, u dot v, this is 5 times negative 1 plus 1 times 0 plus 3 times 2 plus negative 2 times 6. Okay? So this is equal to negative 5 plus 0 plus 6 minus 12. Okay? So this is minus 17 plus 6. This is equal to minus 11. So this is the dot product of those two vectors. Okay? Question. So dot product, it's again component-wise multiplication and then you add the products. Okay? In R2 and R3, you can use this information here in order to find the angle between them, between the two vectors. Similarly, until Rn, okay? In order to find the angle between two vectors in Rn. Okay, you have to find the dot product, you have to find the magnitude of each vector. Okay, and then you do the division. You will get the cosine of the angle. Okay, so what am I saying there? Let me go back to this. So this guy here. So you can find cosine theta will be equal to u dot v divided by magnitude of u, magnitude of v. So you will find cosine theta. So that's how we determine the angle between vectors in higher dimensional space. Okay? Question so far? So these are just simple computations. Some properties, okay, of this dot product. So we get u, v, and w vectors in Rn, k a scalar. So dot product is commutative. u, v, u dot v equals v dot u. So you can interchange them. And it is derived by the commutativity of usual multiplication. You know that 2 times 3 is equal to 3 times 2. So you can, from this formula, you can interchange u1, v1, you can write it as v1, u1. u2, v2, you can write it as v2, u2, and so on and so forth. And that means v is first, and then u is the second. So v dot u. So commutativity is valid, okay, for that product of vectors. Distributive property. So you have a vector u, dot it with the sum of v plus w. Okay, so you will get u dot v plus u dot w. So you can distribute this guy. But take note, make sure to retain the dot multiplier here. Okay, so u dot v plus w equals u dot v plus u dot w. So distributive property. The next property here, we call this the homogeneity property. Okay, so what does that mean? You have the dot product first, and you multiply by scalar k. Okay, so it is the same as when you multiply the scalar k to u first, then you will get a vector ku, then dot it with the vector v. Okay, so meaning you can put this k wherever, either in u or in v. Okay, so homogeneity property. Okay, and then we have the positivity property. So you have the vector v. If you dot it with itself, okay, v dot v, it must be greater than or equal to 0. Okay, v dot v, it must be greater than or equal to 0. And v dot v equals 0, okay, if and only if v is the 0 vector. Okay, so when a vector is dot with itself, okay, then it must be greater than or equal to 0. But if the vector is dot with itself and you get the 0 scalar, then the vector must be the 0 vector. Okay, so positivity property. And later you will realize that v dot v, okay, v dot v, this is actually the square of the norm of v. Okay, I don't know if we will see that later, but I'll show you here now. So you have your v dot v, v dot v. Suppose you are in Rn, so this is equal to, so v1 squared plus v2, sorry, without the square root, So without the square root, so you have v1 squared plus v2 squared plus dot 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 until we have vn squared. Okay? But this is equal to quantity square root of that guy, and then you square it. And by definition, this v1 squared plus until you have vn squared, this is precisely magnitude of v. So the dot product of a vector with itself, it's the square of the magnitude of the vector. Okay? And in fact, this is one of the definitions of the magnitude of the vector. When you dot it with itself, that's the square of the magnitude. Okay? Okay. Next property here, if you dot any vector with the zero vector, so 0 dot v, this is the same as v dot 0 because of the commutativity property. It's the zero scalar. So notice this is bold face because I'm talking about the zero vector. Here, this is not bold face because this is the zero scalar. Okay? Another distributive property. Okay? So u plus v dot w, it's u dot w plus v dot w. So the same as this guy here. But this time we have the right distributive. This is the left distributive, but they mean the same thing. The next property here, if we have subtraction, of course, the subtraction will be retained. Okay, the subtraction will be retained. Similarly for this, the subtraction will be retained. Okay, and this is what I was saying for the homogeneity property. Okay, so you can place your k either with u or with v. Okay, with u or with v. Or you can start with the dot product first before multiplying by k. Okay, so simple properties of dot product. Now, the more bigger properties. So Cauchy-Schwarz inequality, Cauchy-Schwarz. So if we have a vector u, okay, with components u1, u2 until un, and v with components v1, v2, and vn, vectors are in Rn, then if you get the dot product of u and v, you get the absolute value of that, okay, it will always be less than or equal to the product of the magnitudes. Magnitude of u times magnitude of v on the right side of this inequality. On the left side, you have u dot v, then you get the magnitude, okay? So this is the Cauchy-Schwarz inequality. In component form, this means absolute value of u1 plus u1 v1 plus u2 v2 plus until un vn. So that's your dot product. You get the absolute value, okay? This will be less than or equal to u1 squared plus u2 squared plus un squared. Then you take the square root of that. So that's your magnitude of u1. v1 squared plus v2 squared until vn squared. Okay, you take the square root of that. That's your magnitude of v. Okay, so this is the vector form. This is the component form. Okay, so let us verify this Cauchy-Schwarz for these vectors. Square root of 3, 1, and then the vector 2, 0. Okay, so we already know u dot v from the previous example. So u dot v, this is equal to 2 square root of 3. Okay, 2 square root of 3. And then let us see, magnitude of u, this is square root of 3 squared. I think we already got this. This is 2, okay? And then plus 1 squared, this is equal to 2. We also got magnitude of v, this is equal to 2. So magnitude of u, magnitude of v, this is equal to 4. Okay, and indeed, this one is greater than this. Try to check that using your calculator. Okay, try to check that using calculator, but it should be obvious because this is 2 times 2. Okay, 2 times 2, or this is 2 times square root of 4. And square root of 4 is bigger than square root of 3. Yeah? Okay, so Cauchy-Schwarz inequality. Okay? Next property here, we call this the triangle inequalities. If you remember from your algebra, probably, you have seen this triangle inequality. It says you have absolute value of a plus b. Okay, absolute value of a plus b. This is less than or equal to absolute value of a plus absolute value of b. This is just triangle inequalities in the sense of real numbers. Okay? In the sense of vectors, we can extend this triangle inequality as follows. So the magnitude of the sum u plus v, this is less than or equal to the magnitude of u plus magnitude of v. Okay? And you see the similarities. Let me rewrite again that the sense of real numbers. A plus b less than or equal to absolute value of a plus absolute value of b. Okay? Because, well, the sense of real number is just your R1. Okay? It's just your R1. And the square root of a number, it's your absolute value. So this should make sense immediately. So this is the triangle inequality for vectors. For distances, you have the following. The distance between u, v, this is less than or equal to distance of uw plus the distance between w plus v. Okay? Okay? And probably the question is why triangle inequalities? Why triangle inequalities? What does this mean? Why triangle? So you have a vector. Remember, sum of two vectors. If we use the triangle rule, we have the vector u. So the vector u here. You have the vector v here. And this is your vector u plus v. So why triangle? Because it came from the triangle. So this means this longer side here is always less than the sum of these sides here. Okay? This is the shortcut. From this point going to that point, this is the shortest path that you can traverse. U plus V. The long cut is you go to U and then you go to you pass along U and then pass along V. That is longer. Okay? And that's similar to this distance. Okay? Distance between U, V, and W. Because remember, the vectors, they can be represented as the terminal point of a position vector. So meaning, as point, okay, suppose this is the terminal point of U, okay, so let me write this as terminal point for U. This is the terminal point for V. And here, this is the terminal point for W. Distance between U and V, it's this guy here. But the distance between U and W, it's this guy here. And distance between W and V, it's this guy here. Okay? So this path here is much, much longer than this path here. Okay? So distance between U and V, that is less than or equal to the distance between U and W plus the distance between W and V. Okay? And again, triangle. That's why they are called triangle inequalities. Okay? Let us verify these inequalities again. The triangle inequality for vectors U and V. And notice these are the same vectors that we have. So vector, the magnitude of U, we know it was 2. Magnitude of V, this is equal to 2. So if we add them, magnitude of U plus magnitude of V, this is equal to 4. Okay? As for U plus V, so U plus V, so this is equal to the vector square root of 3 plus 2, okay, comma 1. And you get the magnitude of this. Okay. So this is equal to square root of square root of 3 plus 2 plus square of 1. We can simplify this. So this is 9, or this is 3. Sorry, this is 3 plus twice the product for square root of 3 plus 4. And then we have the plus 1 there. And then we take the square root of this. Then if we add them, 8, this is equal to 8 plus 4 square root of 3. Take the square root. Okay. We can manipulate this. And how do we manipulate? We can factor out 4. You take the square root of that. So this is equal to 2 square root of 2 plus square root of 3. Okay. So this guy here is equal to this. Just try to verify. Okay. But this guy here, 2 plus square root of 3, that's again less than 4. Okay. So try to verify that this guy here, this is less than 4. Okay. So this means this is less than 2 square root of 4. Okay. But this is 2 times square root of 4. So this sum here is greater than this. Okay. Okay. So this guy here, so let me write this guy here. This is actually 4. So the sum is less than 4. Okay. So again, it's just a verification thing. You can use your calculator and you will see this immediately. Okay? Question so far? Yep.
So let me understand this correctly, like the math that's being done over here. In the square root column there, the square root of 3 plus 2, that
Mm-hmm.
all that's in brackets is being squared.
Mm-hmm.
Why are we not adding square root of 3 to 2 and then putting the squaring to
No,
that?
because in here, the square root is only on 3, not on 2. We have square root of 3 plus 2.
No, I understand that, but why are we applying the squared to the square root of 3 alone and then to
No, you
the
expanded this to get these 3 guys here.
oh, you expanded it. Okay.
You expanded this to get these 3 guys here.
Okay.
Mhm.
It's expanded form.
Yep,
Okay. Thank you.
you're welcome. Other clarifications? Another big theorem here or property here, parallelogram law for vectors. Okay? So if u and v are vectors in Rn, then u plus b squared plus u minus b squared, this is equal, take note of that, equal to 2 times the square of u magnitude plus the square of v magnitude. Okay? Sorry, if you have the magnitude of u plus b squared plus the magnitude of u minus b squared, it's equal to 2 times magnitude of u squared plus magnitude of v squared.
And the negative just disappears.
It looks like it disappeared, but not really. Okay? It looks like it disappeared. Okay? Graphically, sorry. Yeah.
It's that's a weird theorem.
No, it's not really weird. You will see that here. I'll let you see graphically. So graphically, we use now parallelogram law or the parallelogram method. This is your U, this is your V, and then this is the U here. This is also U and this is also V. So remember that this guy here, it's your U plus V. And then this guy here, it's your U minus V. Okay, so what does this mean? The length or the sum of the diagonals, okay, the sum of the diagonals, it's equal to the sum of the sides. U here, magnitude of U is this. 2 times magnitude of U, it's this U and this U. Magnitude of V, it's just this guy here. 2 times the magnitude of V, it's this guy and this guy. So it says that the sum of the two diagonals of the parallelogram, it's equal to the perimeter of your parallelogram. Okay? It's equal to the perimeter of the parallelogram. So that's the graphical representation. But let us prove this. And we will see that it's not actually weird. It's really nice. Okay, so proof. The proof is really simple. I have shown you, so recall, I have already shown you that u dot u, this is equal magnitude of u squared. Okay? Or v dot v, it's the magnitude of v squared. We are only going to use that. How? So you have the magnitude of u plus v squared plus magnitude of u minus v squared. This is equal to u plus v dot with itself, u plus v. Okay, so that's your u plus v magnitude squared plus u minus v dot with itself, u minus v. That's your u minus v magnitude squared. And then simple manipulation, this is equal to, actually, this is just properties of your dot product. So you will have u dot u plus v plus v dot u plus v. Okay, that's for the first guy here. And then for the other one, you have plus u dot u minus v minus u, v dot u minus v, u minus v. Okay, distributive property. Again, distribute again. So you will have u dot v, u dot u plus u dot v. That's the first guy. And then for the second guy, you have v dot u plus v dot v. I hope you are seeing now what will cancel out. And then here we have another plus u dot u minus u dot v. Okay, then for this guy now, minus v dot u, and then here minus minus, so it becomes plus. So plus v dot v. So notice, so this guy will cancel this guy will cancel this guy. What remained were u dot u, v dot v, u dot u, v dot v. And that's your twice u dot u equals, so twice u dot u plus twice v dot v. And that's precisely your 2 times, so factor out u, and you will have magnitude of u squared plus magnitude of v squared. So it seems like the subtraction disappeared in here, okay? But because of this cancellation, okay, that subtraction was removed. Another property here, polarization identity for vectors. So it says that if you take the dot product of u dot v, it's equal to 1/4 of u plus v squared minus u minus v squared. I mean in magnitudes, okay? So u dot v equals 1/4 of the magnitude of u plus v squared minus the magnitude of u minus v squared, okay? And in order to see this, so I'll leave this to you as an exercise. In order to see this, you will only use the same technique as this one. Okay, the same technique as this one. Instead of a plus, we now have a minus here. Okay, we now have a minus here. So if you do that, you will get 4 times u dot v, or the 1/4 now if you move it onto the other side. Okay, so try to work on this. Very much similar computation as in the previous proof for parallelogram laws. So again, verify the identities. So you can do this. Again, it's a verification, and I have 98% that I will not ask you to verify something. Okay. Let us relate this dot product as matrix multiplication. First one. So matrix, you are considering n by 1 or 1 by n vectors. So n by 1 column vector or 1 by n row vector. Okay? So suppose u and v are both row vectors. Okay? You can still get the dot product of u and v, and that's equal to this formula. U times v transpose. Okay? Take note, row vectors. Okay? So for u, it's a row vector. So u here, it's a row vector. V also is a row vector. So if we get V transpose, you will get a column vector, right? So U, V transpose, you will have the row vector multiplied to a column vector. And you will see this is just a number. So first here multiplied to the first here, plus the second here multiplied to the second here, plus until you have the last here multiplied to the last here. So you have that. Or similarly, you can have V times U transpose. Okay, so this is the same as V times U transpose. So row vector times column vector also. So here you have U transpose is also a column vector. Okay, so if they are both row vectors, you can apply the dot product. Okay, because they are of the same dimension. So U dot V, it's U V transpose or VU transpose. If they are both column vectors, the transpose is on the first side. Okay, so U dot V, it's equal to U transpose B transpose. Okay, so if they are both column vectors, they are both vertical. Okay, they are both vertical. This guy here, say this is your U and this is your V. They are both vertical. So U transpose V, U transpose V. So U transpose becomes horizontal, meaning a row vector. Okay. So you have this dot product. If U is a row vector and V is a column vector, then you just have U dot V equals UV, because this is already row, this is already column. Okay. And if you get the transpose, column vector becomes row vector becomes column. So V transpose U transpose. Okay. So this is for U row vector, V column vector. And the last thing, if you have U column vector, V row vector, you start with the row, multiply the column. If you want to start with the vector U, you have to make it a row vector first. So you have the U transpose. V is a row vector, you have to make it a column vector. So V transpose. Okay? So you would know when you have the actual matrices written in as row or column vector, you would know how to work on that. Because you need, in order to get that, you need a row vector multiplied to a column vector. Okay? So you would know how to work at that. This is your dot product. But now, suppose we have an n by n matrix. Okay? So A is an n by n matrix. U and V are n by 1 column vectors. Okay? Then we can also apply this dot product. So A is an n by n matrix. So A, it's an n by n matrix. U and V are n by 1 column vector. So U, this is an n by 1 column vector. Also for V. So notice if you have AU, this is a column vector. Okay? If you multiply your n by n matrix by a column vector, this becomes a column vector. Okay? So if you have A, U dot V, okay, you will have to get the transpose of AU. Okay? You will have to get the transpose of AU and multiply to B. Because transpose of AU, this is what? A row vector, and V is a column vector. Okay? It is the same as. It is the same as now. Look at this. A dot A transpose V. Okay? A dot A transpose V. So A transpose V, okay? A transpose V, this is a column vector. But look at this guy here. Look at this guy in here. The rows for A becomes columns, okay? And the columns for A become rows, okay? Because you have to get the transpose. So this A transpose V is definitely not the same as AU, okay? Unless A is symmetric, U and V are the same, etc. Okay? But this A transpose V is still a column vector. Okay? And therefore, A or U dot A transpose V, this is equal to, I don't have enough space here. Let me erase this guy, this part here. So U dot A transpose V, okay, this is equal to U transpose A transpose V. That's our definition. Because this guy here, this U here becomes a row vector. Okay? U is a column vector, A transpose V is another column vector. Okay? So if we apply the dot product using the previous slide, this is what we should do. Okay, this is what we should do. But notice, multiplication of matrices, they are associativity, or it is associative. So meaning, this guy we can group together. A transpose A trans U transpose A transpose times V. Associativity. Okay? But transpose, property of transpose, you will have to interchange. Okay? You will have to interchange them before getting the transpose. This is multiplied to B. And notice, this guy here is precisely this guy. Okay? So this is AU dot V. Okay? So this is precisely the proof for this first line here. So U dot A transpose V is equal to, by definition, U transpose times A transpose V. So this dot multiplication, this is dot product, here matrix multiplication. Okay? So let me write that part. So here, dot product, whereas here, This is matrix multiplication. Matrix multiplication. Okay, so dot product here, vector times vector. Okay, vector dot vector. Here, matrix multiplication, property associativity of matrix multiplication, property of transpose. Okay, and then definition again of your dot product for matrices or for vectors. Okay, so this is actually a proof for this one. You can do the same, similar proof for this. You can do similar proof for the second line. This time you can start with this, okay, or with this, whatever, and then you use the definition here. These are the definition there. Okay, so we just use this dot product as matrix multiplication. Okay, so this will be my last example. We can verify the identities. What we can do, so a dot u or au, you multiply au first, and then you dot it with v, and then the other side you multiply a transpose v, okay, and then dot it with u. So this will be my last example, so bear with this extension. So au, let us have au first. Au, this is equal to so 1, negative 3, negative 1, 3, 2, 1, 4, and 0, 1, 1. We multiply this with the vector u, 1, 1, 2. So here, let us do the multiplication. You have 1 times 1, that's 1, plus 1 times negative 1, that's minus 1, plus 3 times 2, 6. Okay? And then second row times this vector, 2 times 1, that's 2, plus 1 times 1, that's 1, plus 4 times 2, that's 8. Then the last vector, you have 1 times 0, that's 0, plus 1 times 1, that's 1, plus 1 times 2, that's 2. So the column vector here, we will get 6, 11, 3. Okay? So AU, that's AU. So AU dot V, AU dot V. So this is what? AU transpose V, but AU transpose is 6, 11, 3 dot with or multiply with negative 2, 0, 1. So this one is equal to what? Negative 2 times 6, that's negative 12. 11 times 0, that's 0. 3 times 1, that's 3. So this is equal to negative 9. Okay? Okay. So save this, and then we'll do this side here. So we get A transpose, multiply it to V. So A transpose V. So first A transpose, we have 1, negative 1, 3, and then 2, 1, 4, and then 0, 1, 1. Multiply this to V. V, it's negative 2, 0, 1. So let us do the multiplication. Negative 2 times 1, that's negative 2. 2 times 0, that's 0. 0 times 0, that's again 0. And then negative 2 times negative 1, that's positive 2. 0 times 1, that's 0. 1 times 1, that's 1. Then negative 2 times 3, that's negative 6. What's next? 0 times 4, that's 0. And then 1 times 1, that's 1. So this is equal to, please check my arithmetic. So this is the column vector negative 2, positive 3, negative 5. Okay. And lastly, we have u dot A transpose V. So this is equal to U transpose A transpose V. Okay. U transpose will be 1, 2, 1, 2, 1, 1, 2. And then A transpose V, it was negative 2, 3, negative 5. So I hope we have the correct subtraction in here, or we have the correct arithmetic there. This is negative 2 plus 3 minus 10. Indeed, we get negative 9 in here. So negative 9. So same as the previous result. Okay? So again, this is just verification. Okay? It means that the equality is true for these examples. The proof, if I ask you to prove it, it must be true for any kind of example. Okay? Try to verify this inequality for you. Okay? U dot AV. So get AV first, then dot it with U. And then the other one, A transpose U. You get A transpose U, and then dot it with V. You should get the equality. Okay? So that will be the end of the lecture for today.